In today's topic, we are going to see some applications of Cayley-Hamilton theorem. We all know Cayley-Hamilton theorem. Every square matrix satisfies its characteristic polynomial. Means, suppose some matrix A, its characteristic polynomial is Ca of lambda. Then Cayley-Hamilton theorem says that Ca of A is always 0. Okay. Now there are mainly two types of applications that we will see. First application is we can find out A inverse of matrix very easily using Cayley-Hamilton theorem. As we all know, formula of A inverse is A inverse equal to 1 upon determinant of A into adjoint of A. We all know how to difficult find out adjoint of A. In adjoint of A, we first find out cofactors. Then we arrange the cofactors in adjoint matrix, take transpose, then we get adjoint of A, then we find out determinant of A. But if we have Cayley-Hamilton theorem, we can find out A inverse easily. We will see second application in our second example. First example. Let A equal to 2 1 1 1, this matrix 2 1 1 1. Cayley-Hamilton characteristic polynomial is determinant of A minus lambda I. Now for any 2 by 2 matrix you can use this formula directly. This and this both are same for only 2 by 2 matrices. So I can get here lambda square minus trace. Trace is nothing but sum of diagonal elements. So 2 plus 1 is 3, and determinant is 2 minus 1 is 1. Okay, so I will get here characteristic polynomial is lambda square minus 3 lambda plus 1. Now using Cayley-Hamilton theorem, what we have? We have Ca of A is 0. That is, we replace this lambda by A. I will get 0. So here instead of lambda square, I write down A square. Instead of lambda, I write down here A. Instead of 1, I write down here I, because A square is matrix, A is matrix. But if I write here 1, it is in some value, it is not matrix. So instead of 1, I write down here I. Now take out I on the right side. So I will get A square minus 3A equal to I. Now if I take A common, I will get A times A minus 3I is minus I. Now I will take this A on RHS. So I will get A inverse with sign of minus I. So it is minus A inverse. So I can say that A inverse is nothing but minus A plus 3I. Simply minus sign goes on this side. So minus A plus 3I. Now for finding A inverse, I require only minus A plus 3I. I have to do only this calculation, minus A plus 3A. Now it is easy because already I have A. So I write down here, and 3I. I is nothing but identity matrix. So by adding this term, we know how to add this term. This term adds to this term. This. Okay. So I will get here A inverse is this. Now we will see the second example. Second example is for your homework. Now it is 3 by 3 matrix. Given matrix is of order 3. So characteristic polynomial will be a polynomial of order 3. So maximum power will be lambda cube. Now here I have given you hint, so you can check it at your home. First find out characteristic polynomial. It will be lambda cube minus 4 lambda square plus 6 lambda minus 3. After that, if you use Cayley-Hamilton theorem, you will get A cube minus 4A square plus 6A minus 3I if you do the same calculation as I do in first example, you will get A inverse is 1 upon 3 a square minus 4a plus 6i. Now here I have to find out A inverse. I have to find out only a square. So if I have a square, a and I can find out A inverse easily. Now we will see the main application. Suppose A is any matrix. Use Cayley-Hamilton theorem to evaluate matrix expression as a raised to 5, 7 a raised to 4, minus 9 a raised to 3, minus 8a square plus 15a plus 4i. Now I will say this all polynomial as p of a, that is polynomial in variable a. So I write down here p of a. Note this word p of a. Now what is the application here? If I have to directly find out this p of a, then I have a, then I will find out a square. Now you know matrix multiplication is a huge complex, it has huge multiplication, huge counting. So finding a square is okay, but finding a cube is nothing but a square into a. Now finding a raised to 4, finding a raised to 5, so it takes a last time. To reduce all this, we have this Cayley-Hamilton theorem. Now first we have to find out characteristic polynomial. You can find out this as we have discussed in our last lecture and also in solve problem session. Now we have to find out p of a. Now instead of p of a, firstly let it as p of lambda. So replace a by lambda. So I have this polynomial lambda cube, lambda raised to 5, 7 lambda raised to 4, minus lambda cube, minus 8 lambda square plus 15 lambda plus, now instead of 4i, I written down only 4. Now we have two polynomials. Which two polynomials? We have p of lambda and characteristic polynomial in lambda. So this is one equation and this is second equation. What I do? Now I divide p of lambda by ca of lambda. We get, as we do in our school study, I divide this p of lambda. So I write down here p of lambda and I divide this p of lambda by ca of lambda, and I find out this is quotient and this is remainder. Okay, so if I do all this calculation, firstly I will multiply by lambda square, I will get this. Then I multiply by 9 lambda, I will get this. Then I multiply by 12, I will get this. So remainder is 41 lambda square. Now when we have to stop, here we are dividing by lambda cube. Highest degree is 3. Here highest degree is 2. It is less than 3. So I will stop here. So if I write down all this, as we know, suppose here some polynomial b, here it is a, here it is c, and remainder is d. Then what we have? We have a is equal to b into c plus d. Similarly, now instead of a, I have p of lambda. Instead of b, I have this ca of lambda. Instead of c, I have this quotient. I write down here, and d is remainder now. Remainder. So I write down here. Now replace lambda by a. Why? Because we have to find out p of a. We have to find out p of a, not p of lambda. So I write down here p of a. Similarly, all changes. Let's change in lambda. Lambda becomes a. Here also lambda becomes a. Here also I write down a. Now where we use Cayley-Hamilton theorem? Now here we use Cayley-Hamilton theorem. As ca of a is 0, as we all know using Cayley-Hamilton theorem, Ca of A is 0. Every square matrix satisfies its characteristic polynomial, so Ca of A is 0. So as this 0, the whole product is 0. So the term remaining only is P of A is 14A square plus 33A minus 20I. Now here, why Cayley-Hamilton theorem is important? I have to find out A raised to 5, but I reduce my efforts to finding it up to A square. Okay, suppose instead of A raised to 5, if they find out A raised to 50, then also we will use the same method. Okay, because every time, suppose there is a 3 by 3 matrix, characteristic polynomial will be obviously in maximum degree will be obviously 3. So as maximum degree is 3, the remainder will be the maximum degree of 2. Yes, so I have to find out here A raised to 50. But using division algorithm, P of A is always remainder, and remainder is always less than degree of matrix. So always it will be of maximum order will be up to 2. So every time I have to find out only maximum term A square only for 3 by 3 matrix. For 4 by 4 matrix, the maximum term I have to evaluate will be only A raised to 3, obviously less than order of matrix. Yes, it is helpful to us. So if we do all this multiplication and addition, we will get this our required matrix. Okay, now here is the main problem. Suppose I have to find out A raised to 300. Now A raised to 5, A raised to 4, it is okay, we can do it directly also, but finding A raised to 300 is not an easy task. It is not an easy task. Here we can see similarly same. Firstly, find out characteristic polynomial. Using Cayley-Hamilton theorem, we have Ca of A is 0. Now finding A raised to 300, we let some polynomial P of lambda equal to lambda raised to 300. Now we apply division algorithm to lambda raised to 300 and our characteristic polynomial lambda square minus 5 lambda plus 4. So what we have, we don't have to calculate, we have to do it as it is. We know, as we all know, dividend equal to quotient into divisor plus remainder. We use this formula. So here dividend is lambda raised to 300. Sorry, this is, I think this is quotient and this is divisor. Divisor is lambda square minus 5 lambda plus 4. We will get some quotient Q of x and R of x. Now R of x plays an important role here. Why? Because degree of R of x is always less than the order of matrix. Here order of matrix is 2 by 2. As order of matrix is 2 by 2, Cayley-Hamilton theorem, characteristic polynomial will be in order 2. If matrix is 3 by 3, we have first term will be lambda 3. If we have 4 by 4 matrix, in characteristic polynomial we will have lambda raised to 4. Okay, so degree of R of x is always less than the order of matrix or maximum degree of characteristic polynomial. as it is, as here matrix is of 2 by 2 order, degree of R of x is obviously less than 2. So in general I will let it as R of x equal to ax plus b. Okay, now here you can note that the degree is 1, x raised to 1 and x raised to 0. Okay, if degree of R of x is less than 3, suppose matrix is 3 by 3. Okay, so degree of R of x will be less than 3, then my assumption of R of x will be ax square plus bx plus c. We will use this for only 3 by 3 matrix. Now let R of x is ax plus b. Now again, now I will rub this all dividend, quotient divisor and remainder. And lambda raised to 3, it is lambda square minus 5 lambda plus 4 times q of x plus ax plus b. Okay, now let's see. Now lambda raised to 300 is nothing but lambda minus 4 into lambda minus 1, as lambda square minus 5 lambda plus 4 is nothing but lambda minus 4, lambda minus 1, I write down here, lambda minus 4, lambda minus 1 into q of x plus ax plus b. Now if we equate ca of lambda equal to 0, I will get lambda minus 4 into lambda minus 1 is equal to 0. So I will get here roots lambda minus 4, lambda is 4 and lambda is equal to 1. Equate this equal to 0, this equal to 0. So lambda minus 4 is 0, so lambda equal to 4, and lambda minus 1 equal to 0, it will give lambda is equal to 1. Now use these two roots, we will say it as our roots. Okay, now use lambda equal to 4 in equation star. This is our equation star. So I will get 4 raised to 300, instead of lambda put 4, so 4 raised to 300 equal to 4 minus 4, it is equal to 4 minus 4. Then in here instead of lambda we will put 4, so 4 minus 1, here it will be q of 4, here it is 4a plus b. Now this term again becomes 0, so the whole term again becomes 0. So 4 raised to 300 is nothing but 4a plus b. Only remainder remains. So I will get this my first equation. Now if I put lambda equal to 1 in equation star, I will get 1 raised to 300, 1 minus 4, 1 minus 1 into q of 1. In first this term becomes 0, now this term will become 0, so the whole term is 0. So only remaining terms are 1 raised to 300, that is 1 equal to a plus b. Now if I solve these two equations simultaneously, I will get a is this and b is this. Okay, so again I will write equation star. So equation star is as it is. Equation star is as it is. Now here we have ax plus b, but instead of ax plus b I write down the value of a. Value of a is here 1 by 3, 4 raised to 300 minus 1 into x, ax this is a, this is x plus this whole term is b. We have find out here ax plus b. Now we have to find out a raised to 300. So we replace lambda again by a. We will get a raised to 300 is equal to, now the first term, this is characteristic polynomial. So characteristic polynomial will become 0 if we replace lambda by a. So this is characteristic polynomial, c a of a is equal to 0. So the whole term becomes 0. The output is, remaining terms is this remainder. Okay, now here instead of a I replace the matrix, instead of I replace this matrix. If we do all the calculation, we will get our required matrix. Now here while multiplication 1 by 3, here 1 by 3, so 1 by 3 takes common. Now this whole term multiplied to this, so I get 2 into 4 is to 300 minus 1. Similarly, multiply this term to the first coefficient. So 1 times 4 minus 4 is to 300. Add this term and this term. So I write down here as 2 times 4 is to 300 minus 1 plus 4 minus 4 is to 300. Similarly, you can do for the remaining term. By adding, we will get this output. Okay. Now, these types of problem are mainly asked in our university exam. So do practice for all this. The one exam, either this type of example or power example is usually asked in our exam using CHT. CHT is Cayley-Hamilton theorem. This is all your homework. Please go through it. Evaluate a raised to 300 for this matrix and also find a raised to 300 for this matrix. What we have to do? We have to first find out characteristic polynomial. Then we have CA of a. Then put this as some polynomial lambda raised to 300. Use division algorithm and carry forward. The process, the required process for doing all this calculation is explained in our theory notes. Please go through it. Thank you.